So we left off the last time talking about methods of making carboxylic acids. And that's relevant here because this chapter is about carboxylic acids and derivatives of carboxylic acids and other compounds that are kind of like unto carboxylic acids in many ways. So it's certainly relevant to ask and answer the question of how you can make carboxylic acids. And we know at least one way already. We learned in chapters 7 and 9 that primary alcohols and aldehydes, either one or the other, can be oxidized to carboxylic acids using Jones reagent, which is essentially chromic acid. It's like H2CrO4. Any strong oxidizing agent involving highly oxidized manganese or chromium will do the trick. Potassium permanganate would also work, by the way. Any of these really nasty reagents that involve, like I said, very highly oxidized chromium or manganese will certainly do the job for us. And if you need to review those reactions, those are back in chapters 7 and 9. So I've given you the addresses over here. There's another way of making carboxylic acids, which is that you can take a nitrile and hydrolyze it. Generally, this requires heat. Sometimes they mention it, sometimes they don't. Normally, I expect reactions like this to be kind of endothermic, but be that as it may, if you add a nitrile to dilute aqueous acid, and remember when we say H3O+, remember that that means it implies that H2O is also present. So Al will sometimes write that, by the way. They'll sometimes write H2O, comma, H3O+. I'm not a fan. To me, it sounds redundant. You can't have H3O+ ions without water around. So maybe I'm being picky, but I just thought I'd let you know. H3O+ implies that water is also present. And you will wind up getting the corresponding carboxylic acid. By corresponding, I mean it will have the same number of carbons, and what had been the nitrile carbon becomes the carboxylic acid carbon. The nitrogen in the nitrile winds up in a molecule of ammonia in the end when everything is done. So of course we're not destroying matter, right? We follow the law of conservation of mass. So that's one way of doing it. And the reason I bring up nitriles is we do know a very good way of making nitriles. We can do an SN2 reaction on an alkyl halide, preferably primary. So X here will be a halogen, iodine, bromine, or chlorine would all work. Treating with sodium cyanide, the cyanide ion is an excellent nucleophile. Remember again that when you see an alkali metal salt, remember that the alkali metal ion is just a spectator ion. It's not going to play any role in this reaction whatsoever. It's just going to float around and watch. So the cyanide ion undergoes SN2 displacement, attacks the carbon that bears the halide. We expel the halide ion, and we get the nitrile. So this is another way of making carboxylic acids that's especially convenient if what you need happens to have a primary carbon over here. These are both of these rather high yielding reactions. I would expect reactions like this to be used in the synthesis industry all the time. So let's see here. I think basically we need to talk about esters today, remind ourselves of what they are, and one of the main ways of making them, though it's not the only way. But other than that, yes, please register your attendance. So I thought I'd give you a break since we had REEF questions on Monday, and besides, this coming Monday is an exam. So that's the plan. Good. So, but any questions on, I think we covered this at least in part last time. I just wanted to make sure I'd clarified all that. Any questions on making carboxylic acids? Trying to think if there are other ways. I think these are the only ways that really relate to what we've talked about already. There sure are other ways, but I think these are the only relevant ones. Good. So let's remind ourselves what esters are. Remember that an ester is, it's essentially the condensation product of a carboxylic acid with an alcohol. And as we'll see in a moment, that's one of the most common ways of making esters. So esters are compounds of this type, and R1 and R2, well, of course, R1 can be either a hydrogen or an alkyl group, so formate esters do exist. R2, of course, can't be a hydrogen, because if it is hydrogen, then you don't have an ester, you've got a carboxylic acid. Is there any way to get exception from final exam? I don't think so. I think I'm kind of required to give it. Sorry. Wish I could. But be that as it may, so compounds of this type are esters. One special kind of ester that you're likely to run into on occasion, these things show up in drug molecules all the time. Esters can be cyclic. In other words, the ester functional group can be built into a ring. And that's a special kind of ester. Cyclic esters are called lactones. And an example of a lactone might be something like this. This is not the only lactone, but all we would do is we would build that ester functional group into a ring. In this case, I'm making a 5-membered ring. So we call cyclic esters lactones. And although your book doesn't mention it, just in case you're curious, cyclic amides are also certainly a thing. So if you replaced the oxygen with, say, NH, you'd have a cyclic amide. That's allowed also. And those things happen to be called lactams. They have a similar name. But your book only really mentions lactones, and I think that's fine. But both lactones and lactams show up all the time in all kinds of antibiotics, all kinds of things like this. They're pretty common. They're pretty common in the pharmaceutical industry. So, but lactones are simply cyclic esters. And let me make sure that I'm not missing anything. Good, and one of the most common ways of making esters is through a kind of nucleophilic substitution reaction on a carboxylic acid. And we're going to look at a few examples of these. And I think we mentioned these earlier. These we could call nucleophilic acyl substitutions. I'll write that down in a moment. But it's important to be aware that these nucleophilic substitution reactions are neither SN1 nor SN2. They go through a rather different mechanism and a somewhat more complicated one, which we're not going to go into all the details, I don't think. But one type of nucleophilic acyl substitution reaction is used a lot to make esters. So nucleophilic acyl substitution. And we'll look at other types of nucleophilic acyl substitution reactions also. Nucleophilic acyl substitution. So that's like the general broad class of reactions that includes this method of making esters. Good. So there are other nucleophilic acyl substitution reactions besides this, but one type of nucleophilic acyl substitution reaction is called Fischer esterification. And yes, that's the same Fischer that we learned about Fischer projections not long ago. He was a busy man. Fischer esterification. And the idea behind Fischer esterification is we're going to do a substitution reaction that involves a carboxylic acid and an alcohol. So in any given Fischer esterification reaction, you'll have some carboxylic acid. We can call it R1CO2H. And we're going to treat that with, ooh, let's do colors. Yes. We're going to treat that with an alcohol, which I'll just call HOR2. And we will heat those things together. By the way, if you ever see a triangle like this, that's shorthand for heat. Just in case you run into it, I don't want you guys to be confused. But you generally need to heat this, and you do require an acid catalyst. So if I were doing this in real life, I think you'll find a lot of times the alcohol is just methanol or ethanol. It's usually a small alcohol like that. I would just take whatever the carboxylic acid is, I'd dissolve it up in the alcohol. I'd add maybe a few drops of concentrated sulfuric acid. I would turn on the heat and let it reflux for a while. Generally doesn't take long, couple hours. And as the product, as the main organic product, you will get the corresponding ester. And that looks like that. And you will also get a water molecule. You can see the H from the alcohol and the OH from the carboxylic acid essentially come together to make water. So water is the inorganic side product. But this reaction is actually in equilibrium. I should maybe have written this as an equilibrium arrow, one pointing this way and one pointing that way. But as long as we exclude water, as long as we don't add like a whole bunch of water, then Le Chatelier's principle will drive the reaction in this direction. Because one of the things Le Chatelier's principle says is that if you remove one of the products, you drive the reaction forward. And I think you'll agree, if we've got this giant lake of alcohol in here, and every so often a water molecule gets spat out from the reaction, well, it's diluted so much in the alcohol, it's as if we are removing it. And by the way, there are also ways of literally physically removing the water. You can add a drying agent, for example, and there are other special equipment. We already have acid carboxylic acid. Why do you need H+? Because remember, carboxylic acids are weak acids. So you do need a strong acid to catalyze the reaction. I think you'll see why when we look at the, well, I won't say mechanism, when we look at the process that the reaction takes. I'm certainly not going to make you guys memorize the whole mechanism complete with curved arrows. It's a bit steppy, but I think we can make some sense out of it by going through the steps and all the different intermediates. And it's going to be a good reminder for us, a good review about reactions that occur under acidic medium, as opposed to reactions that occur under alkaline medium, which we'll also look at an example of that at least today, I think. So, but yes, you do need just a catalytic amount of some strong acid. And like I said, I've done some esterifications in my life, which is nothing special. Doesn't make me a big hero or anything. It's a pretty commonly done reaction. But that's generally how I do it. I would just dissolve up whatever my carboxylic acid is in whatever the alcohol is. Usually this will be methanol or ethanol, maybe not always, but usually. And I just add a little bit of maybe sulfuric acid as my catalyst. Heat it up, go to lunch, come back, it'll be done. That's basically how these things look. So to give an example of a Fischer esterification, let's say that we took benzoic acid and again, you could take any carboxylic acid you liked. And let's say that we treated this with ethanol. Can I go ETOH for ethanol? That's fine, right? If you don't like ET and you want something a little shorter than CH3CH2, you can also put C2H5. That's fine, because C2H5 is unambiguous. There's only one way to put together 2 carbons and 5 hydrogens. So either way is fine. And let's say we then added our acid catalyst and we heated this. I would expect that we would get as our product ethyl benzoate, which is, as the name implies, simply the ethyl ester of benzoic acid. And yes, you will also get water as an inorganic side product, but the major organic product would be the ethyl ester of benzoic acid. So, and I think we can see if we look at the process that this takes, just why we need an acid catalyst. Because yeah, I will say that if you dissolved carboxylic acid in an alcohol, you could heat it forever. Nothing's really going to happen, not at any reasonable speed. So we do need the acid catalyst to speed it up and make it happen in a reasonable time frame. And let me change my share here to your chapter 10 class notes. ET is, let me change that back. ET stands for ethyl. Which is either CH3CH2 or you can also write C2H5, perfectly acceptable. This compound is called benzoic acid. You learned that name in chapter 4. Thinking we're going to get some good review here. If not for exam 4, then certainly for the final exam. So benzoic acid was one of the compounds you had to learn the name of in chapter 4. Ethanol, I think you know. And usually the way we name esters is we name the alcohol component first, which is ethyl, because it's ethyl alcohol. And then we name the carboxylic acid portion as O8, so benzoate. B-E-N-Z-O-A, not sure I'll fit this, T-E. That was close. Ethyl benzoate. But getting back to the actual Fischer esterification process again, this is in your class notes, so I'm literally just projecting your class notes on screen. But I wanted to point out that this was there. This is showing us all the different steps that the reaction takes, because it does take several steps. How many? 1, 2, 3, 4, 5, 6. It's actually not too bad. It's kind of a lot. It's enough that I'm not going to hold you responsible for the mechanism. You'll notice I'm not including the curved arrows here. But this also shows why we need that acid catalyst, because we need to be able to put a proton onto this carbonyl oxygen in order to make the compound react better with the nucleophile, react better as an electrophile. And carboxylic acids are not strong enough acids to do that. We need a much stronger acid than a carboxylic acid. So that's why we need the acid catalyst. At that point, the ethanol molecule attacks this species, and you'll see, just as we've said from the beginning, carbonyl carbons are electron poor. They're electrophilic, right? They have a partial plus charge on them. Even more so when we've put a plus charge on the whole molecule. So ethanol is not the greatest nucleophile in the world, but for something like this, it's good enough. And then here's another good reminder. Whether in this class or in Chem 228, as it turns out, since we talk about this in Organic 2, people will often ask, why can't I just use ETO minus to attack instead of ETOH? Because if I do that, then that'll save me a step. And it's a very understandable question, but there's a very good reason why we cannot invoke ETO minus here, and that's because we're in acidic medium. And we've talked a little bit about this before, but it surely bears repeating. Remember that when you're in an acidic medium, you can't invoke or use any species that are strongly basic, like OH minus or alkoxide ions like ETO minus. Those don't make sense. They can't exist in an acidic solution. So that's why. So at first you do get this intermediate. And then we'll need to do actually a couple of proton transfers. First, we'll take off this one. And you see now we've got this oxygen back to a charge of 0. And then it turns out we need to put another proton onto this oxygen. And the reason why is we're going to lose a water molecule. So this type of substitution goes by kind of an elimination, an addition followed by an elimination. We add the alcohol and we lose water. And so we get, an intermediate that looks like this. This is essentially the product, just protonated. And then something comes along and pulls off that proton, probably an ethanol molecule in case you're wondering, and then we get our product. So these are the steps that we go through. And again, I think you'll see they're fully consistent with us being in an acidic medium. In an acidic medium, we don't ever want to see any structures that are strongly alkaline, nothing with O- on it. Those species don't make sense in acidic medium. Alkaline medium, yes. And we'll look, I think, today at an example of an alkaline medium reaction. And if we get that far today, then we'll look at that. Well, this isn't the mechanism, and I'm not giving you the mechanism. And I already said I'm not holding you responsible for the mechanism. But I think it's helpful for you guys to look at and try to learn at least the steps that it takes. So I'm not going to go through the whole banana with curved arrows. It's a few too many steps for that. But this idea of how a reaction looks in an acidic medium is important, and it's one we've talked about in the past. So even though it's a lot of steps, I think if you at least leave off all the curved arrows, it's not so overwhelming. But you can see that at all times, every step takes place to avoid us getting anything with O- on it. That's why the ethanol doesn't just immediately attack, because if it did, you'd have O- over here. That's why we have to protonate this first. And that's also why we need our acid catalyst to make sure that things like that can happen. And here, likewise, we've got an oxygen with a plus charge. That's fine in an acidic medium. Alkaline medium, not so much. Then we want to avoid things like that. That molecule's neutral, that's fine. This one is a plus charge, also fine. And that's because we're going to lose a molecule of water. Water is essentially a leaving group here. But OH- is never going to be a leaving group, not in an acidic medium. And that's why we had to protonate this first. So once we've done that, now we can lose the molecule of water. At this point, we just have our product protonated, essentially. And a species like that is completely fine in acidic solution. Alkaline solution, not so much, but acidic solution, it's fine. Yeah, and then we get our product. So I think understanding the steps the reaction takes is helpful. And that's also why, that's also going to come up to the next point that I'm going to bring up, which is why we need to use an acidic solution in the first place. Why can't we use an alkaline solution? And it is true, you can only do an esterification like this in acidic solution. Alkaline solution will not work. And there's a very good reason why, which I pointed out on the next page, which is, let's just say we took some carboxylic acid and dissolved it up in some alcohol and added some hydroxide, some sodium hydroxide or something. Well, all that's going to happen is the hydroxide ion will deprotonate the acid. We already know that can happen. We talked about that in chapter 15 when we talked about making soaps. We said that you make them by deprotonating carboxylic acids with either sodium hydroxide or potassium hydroxide, depending on whether you want to get a solid soap or a liquid soap respectively. And so that's all that will happen. The hydroxide will deprotonate the carboxylic acid, which is not the strongest acid in the world, to be sure, but with a strong base like hydroxide, it's more than strong enough. And you get this carboxylate ion, and then you're done. Nothing further can happen to this. There's no way any nucleophile is going to attack that carbon because the thing already has a full minus charge. It doesn't want any more electron density coming in. And so that's the reason, and again, I gave this all to you in the class notes, but that's why you have to use an acidic medium in order to do an esterification of a carboxylic acid with an alcohol. Now, that's not the only way of making esters, that's true. But certainly this manner of using an alcohol and a carboxylic acid must be done in an acidic medium, and this is the reason why. If the medium were basic, all that would happen would be the base would deprotonate the carboxylic acid and we'd be done. Nothing further would happen. So I think all these things are kind of important. I think it's useful for you guys to get out of this class some idea of the difference between a reaction that takes place in an acidic medium and a reaction that takes place in an alkaline medium. And actually, I see we're coming on to saponification or hydrolysis of esters. Now, that one can be done under either acidic or alkaline conditions. But as we'll see, the process is somewhat different. Again, I don't care if you know the mechanism with all the curved arrows exactly. But we'll at least go through the steps. And I think you'll see that there's quite a difference between a reaction that occurs in an acidic medium and one that occurs in an alkaline medium. Even if they both give the same product, the process looks different. So that's really the major point I'm going to make here. Good. I think that's all I really need to say about that. And honestly, I don't think I'm going to push it anywhere past this today. If we can get through hydrolysis of esters, then we'll be in good shape for today, I think. Good. Let me go back to the, where is it? Back to my whiteboard. Or maybe I should go back to this. Again, I can't call this a mechanism. It isn't, because it doesn't have any curved arrows, but back to this scheme. Any questions on Fischer esterification? And I mean, I can do another example if need be, or we might be able to do one later if there's time. This is just one example. This could be any carboxylic acid and any alcohol, and you could get an ester. All right, well, though I have this here, I'd like to go back just for a moment to my whiteboard. So what about the reverse process to forming an ester? Can you take an ester and break it apart into its component carboxylic acid and alcohol? Yes, you can do that. And there's two different ways. This now can be done under either alkaline or acidic conditions. So I'm just going to speak generically here for a moment. Let's say that we have some ester. R1 and R2 can be whatever we like. You can hydrolyze the ester in aqueous acid. So the difference between this and the Fischer esterification was there we had essentially the alcohol as our solvent, and we just added a catalytic amount of acid, no water. This is the exact opposite of that. Here we're dumping in a whole bunch of water and a little bit of acid. And these usually need to be heated also, but that's the difference. So this is going to be acidic hydrolysis. This is one way of breaking down a carboxylic acid into its component carboxylic acid and alcohol. So this is acidic hydrolysis of esters, and we would expect to get at the end the original carboxylic acid and by the way, just a bit of advice. I may be almost doing you a disservice always drawing the ester in this direction with the oxygen here and the other oxygen here, and the carboxylic acid oxygen here, other oxygen here. Do be certain that you can recognize it if the molecule's flipped around, because sometimes things won't be given to you in the most convenient way. So please don't memorize that it always looks exactly like this and is exactly in that position. That might slow you down. But then we would also get the alcohol, R2OH. Good, and that would be the end result. And I think if you work it out, you can see it's taken up an entire molecule of water. So that can be done under acidic conditions. You can also hydrolyze esters under alkaline conditions, and this is also called saponification, which we talked about in chapter 15. I think it was, yeah, on lipids. Whoops. Oh no, that's right, hydrolysis. And in that case, you would again take your ester, and we'll do an example in a moment with again, not the mechanisms, but I want to take you through the scheme. And typically your first step, this would need 2 steps. Your first step will be probably aqueous sodium hydroxide or aqueous potassium hydroxide, or you can just say OH minus in water. Any of the above, any of the above is fine. You might see any of those variants given to you in the OWL assignment. And at first, what we will get is not the carboxylic acid, but the carboxylate ion, right? The conjugate base of the carboxylic acid. And we would also get the alcohol. That will not get deprotonated by hydroxide. This is not a strong enough acid for hydroxide to deprotonate it in any reasonable concentration. And that's because they're very similar. Water and alcohols are very similar in pKa's. You'd need a much stronger base than OH minus to deprotonate an alcohol. And then if you want to get your carboxylic acid out, all you would do is add dilute acid. So this is not like cooking it in aqueous acid. You would just add some dilute acid, and that would put the proton back on. So it really is a 2-step process if you want to do an alkaline hydrolysis or a saponification of esters. But the first step is generally done with hydroxide ion, and again, either sodium or potassium hydroxide would work fine, and you would dissolve that up in water. You don't always need to heat these quite as much. This seems to, I mean, you can, but I don't know that you necessarily would need to. In any case, that will give you the carboxylate ion, the conjugate base of the carboxylic acid, which then if you wanted to get the free acid back out, you would need to protonate it by adding some acid. And that's pretty common. You would just add that right into the reaction mixture. The first thing that the aqueous acid will do will neutralize any leftover hydroxide. And after that, it will start putting protons onto this oxygen, and you can get the free acid. The reason why you might want to do that is because it's inconvenient to leave this as an ion. It turns out to be very difficult to isolate ions. Even then, you wouldn't just isolate this, you would get like the sodium salt, let's say, of this. And I guess in the soap industry, that's what they do isolate. But if you're not trying to isolate the salt, you would simply acidify, and that will neutralize the base and give you the free carboxylic acid back. Put the proton back on here. It's just an acid-base reaction. This oxygen will just grab H plus off of an H3O plus molecule, and you're done. So both of these will work. And the reason that we need both processes is because, well, let's say that there's some other functional group in R1 or R2 that is sensitive to base, will react with base. Well, then we'll use acidic hydrolysis. Maybe instead there's something in R1 or R2 that's sensitive to acid, that acid would make it decompose. Then we would more choose alkaline hydrolysis. But I'll come back and give examples, because I thought in the class notes we did give an example. I just want to make sure that that we go through this with at least one particular example. Yes, okay, so here you go. Here's our ethyl benzoate that we just made a moment ago. I want to go through the 2 different mechanisms, one in acid and one in base, and I think you'll see some interesting differences between them. And again, the way we know that this is different from the Fischer esterification is because there's lots and lots of water around. You need to know, remember that H3O plus implies that water is present. In the Fischer esterification reaction, there was no water present except for the occasional water molecule that got spat out by the reaction and immediately diluted in this ocean of alcohol. So that's what you need to know. That's how you can tell the difference between a Fischer esterification and an acid hydrolysis of an ester. That's what determines which one you'll get, is whether you've got lots of water, in which case you'll get the hydrolysis and you'll go back to the starting materials, or whether you've got little or no water, and that will rather favor the formation of the ester. So that's important. But in any case, the reaction starts once again by protonating this carbonyl oxygen. And indeed, what you'll find is again, I can't call this a mechanism. Again, this scheme, the steps in this scheme are just the exact opposite of like exact reverse order of the steps in the Fischer esterification. Once we've got that intermediate, now water can attack as our nucleophile. Again, water is not the greatest nucleophile in the world, but with this species, with an already partly positively charged carbon and a plus charge on the molecule as a whole, it's good enough. And so water will attack, and just like before, we'll need to do a couple proton transfers. We need to remove a proton from this oxygen. That gives us this neutral intermediate back. And then we'll put a proton on this oxygen. Why? Because we're going to lose a molecule of, in this case, ethanol. We're going to lose a molecule of our alcohol. And kind of similarly to before, that alcohol molecule is now going to drown in this ocean of water. And it's as if we removed it from the system. And so that will drive the reaction forward. Then you get your carboxylic acid protonated, and we just need something, probably another water molecule, to pull off that proton, and we get our benzoic acid back. So here's our carboxylic acid, and here's our alcohol that we get out at the end. So again, kind of steppy in an acidic medium, which is very often the case. But I'll come back to that if need be. But look how much less steppy it is in alkaline solution. And here I've changed up the ester. I've got the methyl ester of 1, 2, 3, 4, 5, 6 hexanoic acid. So I just changed up the ester. So if you want another example of what it might look like, of what you might be given, this is just a different ester here. But the idea is the same. And if we heated this up in aqueous base and aqueous hydroxide, first step is that the hydroxide ion just attacks. That's kind of similar to things that we've seen before when we talked about the addition of water to aldehydes and ketones. We noted that, which by the way, that's chapter 9, is it not? So that should be fair game for this exam. So maybe after this, I'll review that so we can go over something that's on the exam. But it's kind of similar to this. There's just fewer steps. But that's common in alkaline solution. We don't start by the nucleophile attacking the carbonyl in acidic solution, because otherwise you get O-, and that's not good. You can't have that in acidic solution. But in alkaline solution, bombs away. The nucleophile attacks, and you get an oxygen with a minus charge, and since we're in alkaline solution, that's fine. This now is going to lose the methoxide ion and form this carboxylic acid, which is our product, although it's going to be short-lived, as you'll see. But the methanol will simply take a proton off of water. And again, I'm not good. You're not responsible for the curved arrows, although some of these you probably could guess. But methoxide is alkaline enough to deprotonate water, and that's where your alcohol comes from. There's your methanol. Now, here's the thing. We've just generated this carboxylic acid in a solution with hydroxide. And there is no way that we can prevent the carboxylic acid, even though it's allegedly what we want to get out at the end. There's no way we can prevent these two from reacting. We've talked already how bases can deprotonate carboxylic acids, and so it will. And you'll get the carboxylate ion, the conjugate base of that carboxylic acid, of the hexanoic acid. And that and the alcohol will be swimming around in solution quite happily until we acidify. And again, the first thing the acid will do is neutralize any leftover base, and then it will start putting the protons back onto the carboxylate ion to give us our free carboxylic acid. So kind of like with the hydration of aldehydes and ketones thing, this only looks a little more complicated because you've got a few more proton transfers, but there's certainly far fewer steps than we would see in an acidic solution. That's something I've noticed is pretty generally the case. That when you're comparing a process that can happen in either acidic or alkaline solution, the one in alkaline solution seems to be simpler. There's fewer steps. That's something I seem to have noticed over the years anyway. with that, I think I've covered enough for today. I'm pretty confident we can finish the rest on Wednesday after our exam and then get into chapter 17, which is our last chapter. So I'm assuming that there will be no particular complaint if I do some exam review, since this is something that's on chapter 9 and is therefore a topic that's fair game for the exam. Although I'd have to look back and see exactly which section of chapter 9. Maybe I'll do that. Let's see. Chapter 9. It is in 9.8. So let me clear all this out. I mean, I'm assuming this is good. You guys asked for exam review, right? So it's good that we do this, right? So this is 9.8, where we talked about this. There we said that any aldehyde or ketone, so I'll start off generic, and then we'll get into some specific examples. But this can be any aldehyde or ketone for now. We said that whether you treat it with aqueous acid, H3O+, or you treated it with aqueous base, the end result is the same. You get the hydrate of that aldehyde or ketone. Or at the very least, there's an equilibrium between these species. And you'll get something that looks like this. The result of adding water across the carbon-oxygen double bond. And this one we actually did do the mechanism because both reactions are very short, especially the one in aqueous base. So, but the reason this relates to what we were just talking about is because we have another example of a reaction that can work in either acid or base. And we also had a reaction that we learned today, the Fischer esterification, that only works in acid, does not work under alkaline conditions. And we went over the reason why that is. It's in your class notes. It's because the carboxylic acid would react with the base and then it's dead. It's not going to react any further. Good, so let's look at a particular example. Let's say that we took, well, I'm kind of tired of benzaldehyde, but we'll do it anyway. So let's consider what the mechanism, here we will do the full mechanism because it's much shorter than the other one. Let's consider what the mechanism of forming the hydrate will look like under acidic conditions. So since we're under acidic conditions, just like we saw a few minutes ago, we're going to need to start by putting a proton onto that carbonyl oxygen. And we're going to use a hydronium ion. This here that I'm drawing, that is H3O+. And so we'll just put a proton using a hydronium ion onto that oxygen. I'm also going to get lazy and just do pH for phenyl. Just a reminder, it's C6H5. Good. And so our intermediate will look like this. And now our nucleophile can attack. And the only species we have around that can act as a nucleophile is water. Remember, H3O+ implies that water is present. But we will need to use water and not OH-. There is no OH- present, just like we saw in these other reactions today. Not in an acidic medium. Alkaline medium, yes. And believe it or not, we are almost done. This reaction is much less painful than Fischer esterification. That's why I'm not holding you responsible for the curved arrows. I think that would be a bit much. And again, not that I think there's something wrong with you or you can't do it or something like that. I just don't see any benefit. But there is benefit into understanding the difference between a reaction that occurs under alkaline conditions and one that occurs in acidic conditions. And so we get this protonated intermediate here, and then all we need is a water molecule to pull that proton off for us, and we're done. So it's 1, 2, 3 steps. Not nearly as bad as before. And I think if you compare this to something like acidic hydrolysis of an ester or the Fischer esterification itself, you'll see that there's some similarities. The idea that we're only going to have neutral species and cations, no strongly basic anions. Meanwhile, what would this reaction look like under alkaline conditions? Let's say that instead we took, how about 3-pentanone? And we treated this with aqueous sodium or potassium hydroxide. Well, you noticed this before when we did the saponification, the base hydrolysis of an ester. An alkaline solution bombs away. Nucleophile just attacks the carbonyl. And here our nucleophile is the hydroxide ion. Bam. And we'll get a species with an oxygen with a minus charge, but that's okay because we're an alkaline solution. OH over here now. And once again, that's O minus, of course. Once again, we're nearly done. All we need to do is put the proton back on this oxygen. And here we need to use a water molecule, right? Because there's no H3O plus, not an alkaline solution. And then we're done. So very straightforward, just 2 steps. And there's no further steps after this. We don't have to worry about either of those OHs being deprotonated. Why? Because these are alcohol functional groups. Before, when we hydrolyzed an ester and base, we got a carboxylic acid, which is acidic. These are not particularly acidic. So that's it, just those 2 steps. So again, I think you'll see what I mean. The reaction under alkaline conditions is much more straightforward in fewer steps. But this makes a good comparison to what we talked about here in chapter 10, plus is the added advantage of being in chapter 9, which unless I've completely lost it, is going to be on the exam, right? 8, 9, 16, yep. So that's fair game. And with that, I'm out of time. But there's at least some exam review, so that's fine.